These are the notes for Chapter 11 and a little bit of 12. Primarily Chapter 11 and 12 are looking at the properties of liquids and solids, and we're going to spend almost the entire time talking about the properties of liquids. Solids just a little bit at the end. The main thing we're looking at is like the inter versus the intramolecular forces. So we're mostly going to focus on intermolecular forces. Let's talk about some of the differences between those two things. Intramolecular forces are what holds atoms together, like a group of atoms. So chemical bonds. So the examples that you might want to think about are like ionic, bonds, which again are going to hold a group of atoms with charges, positive and negative, how they kind of interact with each other. And again, that's not a molecule. Ionic is a huge structure. So sodium chloride is an ionic compound, and it is a huge complex of bajillions of different sodiums and chlorides all stuck to each other in a positive-negative attraction. Another example would be covalent bonds. Think water. The oxygen and the hydrogen are sharing a pair of electrons twice. So that is a covalent bond. Metallic bonds. So if you think of like copper, there's all these different copper atoms that are interconnected between the positive nuclei and the decentralized valence electrons, which are shared amongst all of the atoms. Those are metallic bonds. And then there is network covalent, and that is a network. You could look at it, for example, like carbon is a typically good example, which is somewhere similar to like metallic, except that the electrons are not decentralized. They are localized between the two different carbon atoms in a huge network of many different carbon atoms. That's a pretty good example. Okay, so those are, again, you're looking at a huge network of atoms all stuck together. Now, different from that, and this is our main focus for this conversation, is intermolecular forces. Now, intermolecular forces is between two different molecules, like one water molecule to a different water molecule. So I know I'm using the same word in the definition, sorry. Forces that hold molecules, and again, different molecules together. So think of like sugar, one sugar molecule to a different sugar molecule. Okay. At the same temperature, solids will have greater intermolecular forces than liquids and gases. So in general, there we're talking about like any solid, liquid, gas, not the same thing, but different solids, liquids, or gases. The solids, because they are solids, means they have greater attraction to each other, so they pull together and form a solid. Liquids are less so. Gases have very little intermolecular force of attraction, so they don't come together as easily. You have to lower the temperature down or lower the pressure down, increase the pressure to force them together. So they're different from that respect. So solids will have a larger intermolecular forces. And just to simplify this in the future, typically the way we write this is IMF. And when we're doing that, we're typically referring to intermolecular forces. Okay. The state, solid, liquid, or gas, is a balance between the energy of the particles which really we're referring to as temperature, and the attraction of the particles for each other. So you always have that balance between it. So the potential attraction of the particles for each other in comparison to the energy that is in the system, the temperature, that allows them to have elastic collisions and bounce off each other. Okay, let's go back and talk about inter versus intra again. Intermolecular forces are much weaker than intramolecular forces. Otherwise, the compound would simply come apart. So if the inters are stronger, then that's going to pull the molecule apart. So like water molecules will stay together unless something more powerful comes along in inter and pulls the water molecule apart. Intra. Again, the ionic covalent metallic. I'm not going to write that again. Intra, well, I guess I will. Ionic covalent metallic. And the inter, this is the first time we'll be specific here, which is why I'm writing this down, is dispersion, also known as London. Called dip-dip, dipole-dipole. And one of the other ones that kind of goes in this category is hydrogen bonding. Yep. It's supposed to be a B. Hydrogen bonding. So actually hydrogen bonding is a dipole. It just happens to be a very specific strong dipole. But typically we kind of give it its own little category. But it is a dipole, but intermolecular forces specifically. All right, let's keep this rolling. We're going to start off looking at the first one, dispersion. Inter, and specifically dispersion, so something to keep track of is as molecular weight, the molar mass, increases, so does the dispersion. I'm going to say dis. So something you could look at is just anything going down a column on the periodic table, as I got one handy right here. For example, if we want to look at comparable atoms, if we look at the, let's do the halogens. Fluorine, these are all diatomic, and as you're going down the column, this is the gas, this is the gas. Bromine is actually a liquid at room temperature, and iodine is a solid at room temperature. And the reason for that is because of the attractive forces these guys have for each other themselves. So again, we're just looking at fluorine attracted to other fluorines and so on down the column. This is going to have more attraction, and therefore it is going to be a solid in comparison to fluorine, which is very much a gas. Okay. Something else that goes along with this conversation is going to be the shape. It's also really important. So if something is spherical, so which would have more interdispersion, line of dispersion? Something shaped like this, or something that has the exact same molar mass but is shaped like this? So just kind of squishing it down. Which one has more surface area? If your guess is that this has more surface area, you would be correct because it's been flattened out and there's very little interior space in comparison to this one. So the more surface area you can have in a molecule, the more dispersion forces you're going to have. So it's not just the molecular weight, the molar mass, it is also the surface area. So when you look at a molecule, something that has more surface area is going to have more dispersion attractive forces. Okay, and something on your own, which we saw actually, if you take a look at the other PowerPoints I have, we do a pretty good comparison of that. So you can go back and take a look at that if you like. This is probably a good place to stop. So I'm going to go over to and start a next lecture after this.